Okay, let me know when you have things downloaded, okay, and we'll start back up. I have one thumb up. Another thumb up. Do-to-do, do-to-do, do-to-do.
Maybe you just go through it.
Have you downloaded all the stuff for the lab?
Yes.
Yep. Good. Okay, anybody not have it loaded up? We're all set? All right, so you're going to do three things today. You're going to gain an intuition for semi-analytic inversion by doing it by hand or by eye. You can go ahead. Go ahead. Then we can do quantitative inversion using, have MATLAB code to do the inversion. You have the code for my model, the GSM model, the QAA model, the model that Emmanuel and I wrote for retrieving backscattering, and the phytoplankton functional type model. If you don't do MATLAB, then you can either like really quickly translate it into Python, or you should just pair up and work with someone when we get to that point so that you can see how it works. And then I'm also giving you, we probably won't end up getting to it, but called the general something inversion. I can't remember the GIOP, not the GUI. The GIOP model, the generalized IOP inversion model that the Ocean Biology Processing Group put together, which basically does the same thing as the software that I'm giving you, to be able to sort of choose which inversion you want to do, et cetera. So you're welcome to take that with you. So what I want you to do is open up the Excel version, and I think it's called Semi-analytic Inversion, Roesler. And in that, there's the OC4, probably the older OC4 algorithm is in there. There's the eigenvectors from the 95 paper, and 3 examples of reflectance spectra for blue, green, and yellow water. So if you open that up, you'll see something that looks like this. Oh, I never know how to close this. Anyway. Oh, that's right, because I can't see my full screen. All right, so you should have this open. Does everyone have this open? Okay. So I'll have to do it from here. Okay. So, oops. So on the first worksheet, it's the OC4 algorithm. So these are the band ratios. These are the coefficients, C0 through C4. And here's the equation to estimate chlorophyll from the maximum band ratio using the squared fourth term, et cetera. I can't remember, yeah. You can update it if you want, these coefficients. The next one is the eigenvectors. So this is wavelength. There's absorption by water, phytoplankton, CDUM, and non-algal particles. I also give you the opportunity to add the CDUM and non-algal particles together. Backscattering is by water, small particles, and large particles. Everything is scaled to the magnitude at 400 because it's a spectral shape that we're interested in, except for water, backscattering and absorption, which are in real values per meter. You can change the, and these are the graphs of them over here. You can change the spectral slope of CDUM if you want. You could make it 0.02 or whatever you want. You can change the spectral slope of non-algal particles if you want. It will change the steepness of the slope. You can change the slope of averaging them together if you wanted one eigenvector. Small particles have an eta of -1. That's that. The eta is this factor. So that's what determines the spectral slope. That's the BBP for eta equals 0. That's eta equal -1. Particle scattering spectrum. You could change those if you wanted. I'd start off with them just the way I have them at first. And then when you get to here, you have 3 examples: blue water, green water, and yellow water. And what you see at the graphs over on the side, let's see, whoop. Okay, the graph on the side is the measured reflectance spectrum for blue water. And so that's here, wavelength versus measured spectrum. This is the absorption by all the components. So there's water, it's always there. And because I haven't added any of these in, you don't have any absorption or particle backscattering yet. It automatically calculates the band ratios for the measured reflectance. And then it calculates the maximum band ratio and estimates the chlorophyll concentration from the measured reflectance just by doing the maximum band ratio on it. So it's giving you an estimate of the chlorophyll that's in the water. And so based upon the measured spectrum, it says that the waters are really clear. It's 0.05 milligrams per meter cubed. That's just an estimate. This is going to be the estimate of the spectrum that you generate. So, and this is going to tell you how well your modeled and measured spectrum, the correlation between them, and the root mean square error between them. It calculates that automatically. And so what you do is you just start putting in numbers here. And as you start putting in numbers, because the eigenvectors are scaled to a value of 1 at 400, if you want an absorption coefficient of 0.01, you would put 0.01 in here for where these blue zeros are. So as you change this, it will populate this with the magnitude of the absorption and backscattering. And it will calculate a reflectance spectrum, a modeled reflectance spectrum, and it will calculate the statistics over here. So right now, the modeled reflectance spectrum is huge in the blue because the only thing in the model is water, because that's something that you can't change. So just go ahead and type some numbers in, and you'll start to see changes in this spectrum. And your assignment is to come up with the smallest root mean square error. And so it's a competition. No. It's not, but it's sort of like, how much do you need to add to make the spectrum the right magnitude? How much backscattering do I balance with absorption? How much phytoplankton versus CDOM absorption to get the right shape? And so a lot of it is just sort of fiddling around like, whoa, I added too much CDOM, I've got to bring that back down. And so just develop a sense of what you need to do.
Collin?
Yes?
So in a real example, you measure the spectrum, you normalize it in your slide and inversion, and you get the value that you're asking us to eyeball.
I'm not normalizing anything.
You didn't say that you normalize the shapes typically.
Oh, the eigenvectors. So the eigenvectors are just shapes.
Yeah.
I could scale them to be 0.01. I could scale them to be 1 at 440. I could scale them to carbon. They're just a spectral shape. So I'm just having it so that when you put in a coefficient here, that coefficient is actually an absorption coefficient per meter at 400 nanometers.
Yeah.
Right? So the shape, we'll use phytoplankton as an example. Ooh, doesn't really look like that. But here's 400 nanometers. I've scaled this to 1. That's the phytoplankton eigenvector. So if I think that I need to have an absorption equivalent to 0.05 at 400 nanometers, to fit my curve, I think I need about that much. I would enter 0.05 in here. And then what you'll see when you do that is that at 400, this value will be 0.05, and the rest of the shape of the curve will be just this scaled up and down.
Yeah, so basically we're eyeballing the inversion.
Yeah. You are doing a semi-analytic inversion by hand. And the beauty of this is that you can do a really good job. And you can compare it to what you would do with, 500 lines of MATLAB code. And you can do it by eye. And you can get some statistics. And you could generate some uncertainties.
Yeah, I'm just asking, in the field you actually have to measure the eigenvectors if you want
Nope.
to predict.
Oh, no. Oh, I use the same eigenvectors I've been using for 20 years. You don't tune your eigenvectors because you don't need to, right? You should be able to estimate the concentration of phytoplankton and non-algal particles because the shapes of the curves, the variability in the shape of the curve is a second order problem compared to the fact that you have phytoplankton, CDOM, and NAP. But when I went to the Arabian Sea, I didn't put in a curve for Synechococcus because we knew we didn't have any Synechococcus. So I put in a green algal curve that was a good model for the symbionts in Noctiluca, which were green alga. I put in a very strongly varying CDOM absorption spectrum because I know that the CDOM there tends to be closer to 0.02. But I didn't measure it. I just used historical data. So I didn't use any of my samples to derive my model to test my data. Completely independent. And that is actually something to aim for. Again, the physics doesn't change. You don't have to tune this model. Right? These curves were all from a lab. So, yeah. That's what you validate this against. Right? So I put this in. Maybe I measured this from some of the cultures in there. And then when you derive the reflectance and you see some, interesting features in here that it looks like maybe there was chlorophyll B and I didn't have a chlorophyll B containing thing, but I noticed that I've got some residual that sits right here. That's right where chlorophyll B measures. Then I can say, oh, well, I didn't have a chlorophyll B containing phytoplankton as an eigenvector. But that way I can compare it to what I measure on a filter pad, right? And say, oh, my eigenvector wasn't a very good representation, but I got the right magnitude of absorption. Yeah, we're at the one-on-one place. Just go for it. There's 3 different water types, blue, green, and yellow. So then the coefficient that you put here is the spectral average absorption coefficient. I could also have normalized the phytoplankton to chlorophyll, and then the value that you put here would be the chlorophyll concentration. I could normalize CDOM to dissolved organic carbon. So if this was a carbon-specific CDOM absorption, then this value would be the dissolved organic carbon in milligrams per liter. So those curves, it just doesn't matter. It doesn't matter what value you set to them. It's just the shape. And the magnitude of the coefficient is really, the meaningfulness of that depends on how you scale them. Mm-hmm. Yeah. Yes. So these are the RMS errors that I was able to come to. So if you get better than me, let me know. 00353, 3083, and 0053. Ah, good.